Alright, there is a special case of this DFT when n is 2 to the power nu or 2 to the power p. When p is equal to 3, this becomes 8. When p equal to 4, this becomes 16. When p equal to 5, this becomes 32. That's a special case, usually used. Alright, 8-point DFT, 4-point DFT, 1-point DFT. What is 1-point DFT? 1-point DFT is the sequence itself. We will see that in a moment. Once again we will see. Now we will take an example. We have 1, 2, 3, 4. 0, 1, 2, 3, 4, 5, 6 and 7. This is sequence xn, that is periodic. Periodic means 8th value is once again going to be like this. This is our x of n. All these values are 1. The sequence is periodic. All right. Now, when I try to write the corresponding, let's say all are 0 now, only this sequence, only one sequence like this, 4 ones and 4 zeros or other infinite zeros, doesn't matter. How would we represent this? This is equivalently represented in the Fourier domain by a magnitude spectrum. So, we have now n is equal to 4. So, our spectrum is sine of 4 omega by 2 divided by sine of omega by 2. That is the magnitude response. This becomes sine of 2 omega. Sine of 2 omega means like this, two sample values. So, it becomes this is the spectrum from minus pi to plus pi. Or if I write it from 0 to 2 pi, if I write it from 0 to 2 pi, then it will be like this. This is 0, this is 2 pi, this is plus pi. So, whatever exists from minus pi to 0 will appear here. So, minus pi to 0, whatever was appearing, it appears here as well. It is periodic function. So, it repeats. Now, I will consider only the sample values between 0 to 2 pi. So, this is my capital X e to the power j omega. Now, what I am going to do is, this I am going to sample at what instance? Now, since I am now choosing only 8 values of the sequence xn, xn exists from only 0 to 7, where 0 to 3 is constant 1 and 4 to 7 is 0. When I take this sequence, that means I am choosing now n is equal to 8. N equal to 8 means what? What is omega k? Omega k is 2 pi by 8, means pi by 4. So, now my frequencies here are 0, pi by 4, pi by 2, 3 pi by 4, pi, 5 pi by 4, 6 pi by 4, that is 3 pi by 2 and so on. Alright, and last one is 6 pi by 8, sorry 7 pi by 8, 3 pi by, this is 6 pi by 8, 6 pi by 8, that is 3 pi by 4 and so on. So, pi, then it is 5 pi by 4, 6 pi by 4, this is what is 3 pi by 4, this is what is 2 pi by 4, which is pi by 2. So, I am dividing 2 pi by 8 equal samples, equal length samples, equal. So, 2 pi is divided into 8 equal values. So, 2 pi by 8 is the sampling value. So, 0, 2 pi by 8, 3 pi by 8, sorry 4 pi by 8 and so on. So, when omega k equal to 2 pi by 8, what is omega k? It is 2 pi by 8 into k, that means pi by 4 into k. So, when k equal to 0, it is 0, when k equal to 1, it is pi by 4, k equal to 2, it is pi by 2, k equal to 3, 3 pi by 4, k equal to 4, 4 pi by 4, which is pi, 5 pi by 4, 6 pi by 4, 7 pi by 4 and 8 pi by 4. 8 pi by 4 is not to be considered because that is repeating value. That is the same value at n equal to k equal to 0. So I have to vary k from 0 to 7. Alright. Now the samples are these 1, 2, 3, 4, 5, 6, 7, 8. That is all. These are the 8 sample values. So now my Fourier transform looks like 1, 2, 3, 4, 5, 6, 7 and 8. This is 0, 1, 2, 3, 4, 5, 6, 7. This is what is mod of xk, which is nothing but an 8-point DFT of the sequence xn, which contained 4 ones and 4 zeros. This could be periodic. When it becomes periodic, this also becomes periodic. Alright. Discreteness here makes this periodic. But when I am sampling it, that means I am making it discrete here. This becomes periodic. Periodic in one domain makes the spectrum discrete. Discreteness in this domain makes it periodic here. Alright. So that is nothing but an n-point DFT. So explaining this once again, we have xk, which is defined as n-point DFT of a sequence xn, which is equal to summation of n going from 0 to n minus 1 x of n e to the power minus j 2 pi by k 2 pi by capital N times k times n. Here for simplicity, we assume we write a new symbol called Wn, which is equal to e to the power minus j 2 pi by capital N. Then I can write this as summation n going from 0 to n minus 1 xn times Wn to the power kn. A simpler symbol, simpler notation. Friends, DFT is being defined as, we have seen that any function that is aperiodic, set of samples un minus n, we have seen that this is represented in the form of Fourier domain representation, which was periodic here, continuous and periodic. For n odd, one typical case we have seen like this. So what happened here? This sequence is x of n is aperiodic, is discrete. How is this obtained? This is obtained by sampling in the time domain. So as soon as we sample it, this became periodic. What was the Fourier transform of an aperiodic continuous time function? It was continuous frequency, but existing from minus infinity to plus infinity. CFT, continuous Fourier transform, the signal and the Fourier transform both exist from minus infinity to plus infinity. Both are continuous, both are aperiodic. So aperiodic continuous function represented by aperiodic continuous function. That was CFT, continuous Fourier transform. If you recollect, let me put down that slide again. See here, the signal here is continuous time periodic, x of t is periodic. Fourier initially said that any periodic function can be satisfying Dirichlet condition can be represented in the form of harmonically related frequencies. So this became discrete. This is periodic, this is discrete, but existing from minus infinity to plus infinity. this is periodic. This becomes a special case of this, where period is infinity. This is a periodic function with period infinity. So what has happened here? The same set of numbers that were existing, which were called Fourier series coefficient Cn bar became continuous. N omega 0 was replaced by capital omega. So it became continuous function. Continuous of what? Of omega. So this is continuous aperiodic, continuous time aperiodic, continuous frequency aperiodic. That is the representation up to this. This we wanted to do it by digital computer. So what did we do? We said let's replace xt by xn. That means we did t is equal to nt. In the time domain, what we did? This aperiodic signal, continuous time aperiodic signal became discrete time aperiodic. As soon as we made this, what was its impact on the frequency domain? Periodicity was the frequency domain impact. So this x of e to the power j omega, irrespective of whatever be the function, ut, nt, 1, sin omega 0t, sin 2 omega 0t, whatever is the function, this x of e to the power j omega is always periodic with period 2 pi. That's the typical characteristics of discrete time Fourier transform. This was known as discrete time Fourier transform. In discrete time Fourier transform, what happened? This became discrete aperiodic. This became continuous and periodic. Discreteness in the time domain, impact is periodicity in the frequency domain. Now the importance of frequency range has been limited to minus pi to plus pi. Alright? As you see here, on a digital computer, you cannot compute this. You cannot implement this on a digital computer exactly. Approximately you can implement by using trapezoidal rule or by using Simpson's 1/3 rule or Simpson's 3/8 rule and so on. Any integration can be implemented, but there will be always an error. Alright? So these equations, since infinity is not realizable, this equation is not representable. These equations cannot be implemented on a digital computer. So also is this, where it's continuous. Digital talks about only discrete. This cannot be implemented because the function is continuous, so also it is infinite, minus infinity to plus infinity. This is implementable in time domain, but minus infinity to plus infinity you can't go. You have to go from finite to finite value. So this also cannot be computed. So first three forms of equations of Fourier transform are not computable, but the last form, which is discrete Fourier transform, is computable. Computable in the sense everything is finite here. 0 to this, it can be easily computed. This equation can be computed, so also this equation can be computed. A finite sequence, finite length sequence can be represented by another finite length sequence. What I want in sequence representation in general is that I always give an example of the JPEG coding. What is JPEG? A photograph, a raw photograph you take. What is the raw photograph size? Say 1000 pixel by 1000 pixel. Pixel is a picture cell. 1000 by 1000. How much space does it take to store on a computer? It takes 1000 by 1000 and 1 byte per pixel. So 1 megapixel, 1 megabytes are required to store a photograph. But we want this to be represented in as minimum number of pixels as possible. So this is a sequence of numbers. Pixels are what? Sequence of numbers. So the size is 1 mega, 10 raised to 6, 1024 multiplied by 1024. That is the size of 1 mega. 1024 by 1024. That is value of capital N. This sequence of numbers we want to represent in as small numbers as possible, where N should be less than the value of the number of samples to be represented. Finite number of samples must be less than capital N. Alright? That is beyond our scope in this course. Here what we are doing is an n-point DFT can be represented by an n-point sequence. Any n-point sequence is represented by another n-point sequence, a transformation. The important characteristics in the time domain, when they are not readable, we go to a transform domain and see those properties, see those characteristics. That is the purpose of transformation. So DTFT was not computable. We have studied that DTFT because that is a Fourier transform of a discrete time sequence. That is why that was known as discrete time Fourier transform, but is not computable. So what do? Like we have sampled in the time domain, let's see the impact of sampling in the frequency domain. So x e to the power j omega, which is a continuous function from 0 to 2 pi or minus pi to 2 pi, minus pi to plus pi, is divided into n equal intervals in the frequency domain. The impact of sampling in the frequency domain is periodicity in the time domain. Time domain sequence was aperiodic. Discrete time aperiodic sequence which gave the Fourier representation in the form of discrete time Fourier transform, which is continuous and periodic. When I sample it, it becomes periodic in the time domain. Xn becomes periodic in the time domain. That is the purpose of studying discrete Fourier transform. What is the aim? Aim is we are representing an n point sequence by another n point sequence, equal number. We wanted it to be represented in as minimum number of samples as possible, but that is not the purpose of this course. In JPEG what happens? 1 megapixel, 1 megabytes of actual raw data in a photograph can be represented in few kilobytes. So n, which was 1 mega, becomes a few kilobytes in JPEG. JPEG also is a transformation. What the JPEG does? N sample values are represented by some k sample values where k is much less than capital N. That is why we get what is known as compression, data compression. Alright. So purpose is an n sample values to be represented by other k sample values where k must be less than n. Here discrete Fourier transform actually determines or actually represents an n point sequence by another n point sequence. Okay. We will see the computation of this. This is computable as I said, but is computable by a digital computer. However, it can be computed fast. So there are fast algorithms for computation of DFT which are called as fast Fourier transform algorithms. Okay. I wish the afternoon class I will take only problem solving, difficulty solving. It seems there are many difficulties as regards to the content so far covered. So let me not take the continuous this I will continue in tomorrow's class. So today's class from 3 to 4 only discuss about your difficulties. Will that be all right? Is it okay? So, but I will not talk on my own anything. You ask me the difficulties, I will try to sort it out. All right?